Welcome to This Explainer. Look, if you're an aerospace engineer designing systems that have to survive literally the most punishing conditions imaginable, you already know that standard materials have a hard ceiling. They melt, they crack, they oxidize. Well, today, we're going to look at a material system that absolutely shatters that ceiling. We are diving deep into boron nitride.
Okay, let's just quickly run through the agenda for this briefing. We're going to cover 1. Introduction to boron nitride. 2. Crystal structures and polymorphs. 3. Manufacturing and processing routes. 4. Thermomechanical and dielectric properties. 5. Aerospace and advanced applications. And finally, 6. Future frontiers and challenges.
All right, Section 1, Introduction to Boron Nitride. We're kicking things off with the absolute fundamental reality of aerospace engineering, that constant, never-ending battle against heat, friction, and radiation.
Boron nitride is basically the engineered solution for these extreme environments. And what's really important to grasp right out of the gate is that we're not just looking at one static material here. It's an incredibly versatile design space. It gives you this frankly amazing combination of extreme thermal stability, chemical inertness, and electrical insulation. Once you really understand this platform, you can bypass the thermal and physical limits that hold back traditional metals and polymers. It's a total game changer.
Moving right along to Section 2, Crystal structures and polymorphs. To truly leverage this material, we have to start at the atomic foundation and understand its structural duality.
Because there's a really stark dichotomy here, and it's fascinating. You've got this wild split between the soft, lubricating hexagonal phase and the super hard, metastable cubic phase. On one side, hexagonal boron nitride, or HBN, is graphite-like. It's sp2 hybridized, making it super soft with a ridiculously low coefficient of friction, which is exactly what you want for a high-temperature solid lubricant. But then, if you put it under extreme heat and pressure, it transforms into cubic boron nitride. Now it's diamond-like, sp3 bonded, and has an extreme hardness of 45 to 50 gigapascals. It's literally the second hardest material known to humanity. Two completely different extremes derived from the exact same elements.
But here's the catch for the hexagonal phase. Anisotropy. Because it has this layered structure, you get a massive trade-off in how it handles thermal and mechanical loads in different directions. When you press HBN powders into a solid part, the weak van der Waals forces between the layers cause those tiny, microscopic platelets to slip, kind of like a deck of slippery cards, and they align perpendicular to the applied pressure. As an engineer, you absolutely must account for this directional dependence in your structural modeling. The material is going to behave completely differently depending on the axis of stress or heat.
Which brings us to Section 3, Manufacturing and Processing Routes. Understanding how we actually synthesize these phases is totally critical for determining if it's viable for manufacturing. So, how do we get from raw precursors to complex, flight-ready hardware?
Enter polymer-derived ceramics. You start with molecular precursors like borazine. People in the field often call it inorganic benzene. And this allows us to actually spin fibers or mold parts before we bake it in pyrolysis. Think about what a huge paradigm shift this is. Instead of just taking raw powders and brute forcing them into a shape, you can use standard polymer processing techniques to mold highly complex geometries. Then you just burn off the organic backbone in a furnace and you're left with a high-purity boron nitride ceramic. It gives you completely unprecedented geometric freedom.
And it gets better. By mixing in other precursors, like these borazine-silicon mixtures, your teams can engineer functionally graded materials perfectly suited for advanced ceramic matrix composites. You can literally tailor the composition on a molecular level. Want to tweak the thermal properties? Mix in some silicon and carbon. You end up with S, B, C, N matrices that meet the exact demanding needs of your specific aerospace application.
Now, what if you are sticking to traditional powder consolidation? Well, there's a hurdle. Normally, you'd need glass-forming additives to densify HBN, but those degrade its high-temperature performance. So spark plasma sintering has emerged as an absolute lifesaver here. You take the powder, put it in a graphite die, apply uniaxial pressure, and then, here's the kicker, you pass a pulsed direct current right through the setup. This causes localized Joule heating and plasma cleaning of the particle surfaces. It creates highly dense, incredibly pure HBN ceramics at way lower temperatures and in a fraction of the time compared to standard hot pressing.
All right, Section 4, Thermomechanical and Dielectric Properties. Let's look at the actual hard numbers. What can this consolidated material survive in the field?
1,000 degrees Celsius. That's the impressive threshold before hexagonal boron nitride even thinks about oxidizing in ambient air. Up to that point, it just forms a nice protective boric oxide layer. And if your systems are operating in an inert atmosphere or out in the vacuum of space, it stays structurally stable up to a staggering 2,000 degrees Celsius. And while it's surviving all that intense heat, it's also incredibly good at moving it. We're talking approximately 130 to 150 watts per meter Kelvin. That is massive in-plane thermal conductivity for bulk HBN, making it an exceptional heat-spreading material. It pulls those intense thermal loads away from your most critical components incredibly fast. But we've got to come back to that anisotropy. The highly directional nature of HBN means you have to orient the material perfectly within your hardware. Notice the thermal conductivity difference here. It's super high along the in-plane layers, but incredibly low, just 20 to 25 watts per meter Kelvin, perpendicular to them. But the real magic is the electrical insulation. That stays incredibly high, over 10 to the 14th ohm centimeters in both directions. So think about that. It conducts heat like a metal, but insulates electricity like a premium ceramic.
Section 5. Aerospace and Advanced Applications. Let's transition from the fundamental specs to direct aerospace deployment. Where is this material actually flying right now?
Because of its chemical inertness, its high dielectric breakdown field, we're talking 10 to 20 megavolts per centimeter, and the fact that molten metals just slide right off it, BN is actively deployed across critical subsystems. We're using it in rocket nozzles, taking massive thermal shock. It's acting as thermal interface materials, or TIMs, for densely packed power electronics, shedding heat without shorting out the boards. It's baked into protective radomes and structural CMCs to drastically improve toughness, and in those crazy high-temperature environments where normal liquid lubricants would just vaporize instantly, HBN acts as a highly reliable solid dry lubricant.
Finally, Section 6, Future Frontiers and Challenges. We need to look at the absolute bleeding edge of material science here, because boron nitride's role is expanding way beyond just passive structural protection.
I love this quote because this represents a massive paradigm shift. Researchers are no longer just trying to mitigate flaws. They are actively, intentionally designing atomic defects in the HBN lattice. Historically, material science has always been about eliminating imperfections, right? Well, now we're purposely knocking out nitrogen atoms or adding carbon atoms to the lattice. Why? Because these specific engineered defects act as stable, room-temperature single-photon emitters. This completely transforms HBN from a bulk refractory ceramic into a customizable, functional platform for next-generation quantum communications and ultra-sensitive magnetic sensors. It's brilliant.
So as we wrap up this explainer, I want you to consider how this transition from a simple bulk ceramic to a precision-engineered quantum platform could completely revolutionize your next aerospace design review. We've covered the fundamental chemistry, the advanced manufacturing pathways, and the extreme thermomechanical limits of this remarkable material. The tools to shape the boron nitride design space are finally here. So the question is, how are you going to use them to build the future of aerospace? Thanks so much for tuning in, and keep pushing those engineering limits.